that, we have another invited talk. Now we have Ido Ben-Shaul, and he's going to talk about neural collapse. So thank you. Can you hear us?
Yes, perfect. I can hear. Can you hear me?
Yeah.
Yes, thank you. Okay. So hi, everyone. Thank you for the opportunity to speak here. My name is Ido Ben-Shaul, and today I'll be talking about intermediate neural collapse and generalization. So this is joint work with Lian Galanti and Tomer Galanti. So I'll start off by defining neural collapse and just giving a quick intro. So Papian et al. Showed in this paper that if we take a large overparameterized neural network in the classification setting, and you train it with SGD and weight decay, several geometrical phenomena happen in the penultimate layer. So we're going to focus on some of them, and mainly that the feature embeddings of samples from the same class cluster around their class means. So in this diagram, if the small balls, if they represent samples from the features and different colors represent different classes, then we're going to see a clustering around their class means. And in this cartoon, we actually see the process between the layers. So they start off random, and we see this clustering around their class means. And at the end, we have something we call variability collapse, where all the points from the same, or all the samples from the same class are mapped to the same point. So why do we care about neural collapse? And can we relate it somehow to generalization? Now, I'd like to point out that we can actually measure the amount of clustering that's happening in the epochs and in the intermediate layers. So we're going to see this soon. So the first question we can ask is, does neural collapse imply generalization? Meaning that if we have some neural network and we check how much it collapses, can we say how well it will generalize to new samples? And in this paper by Tzu et al., they showed that even when we train with completely random labels, we actually get collapse. So here they have CFAR10 with several different networks, and we see that they reach perfect collapse. So one might think that our conclusion is that neural collapse does not imply generalization, and we can go home. So we ask a slightly different question. So maybe neural collapse is indirectly connected with generalization. And our intuition is that neural collapse actually hints at the actual complexity of a trained neural network. So I'm going to formalize this in a bit, but I'd like to give you the intuition. So here we have networks that are trained on CFAR10 with a convolutional neural network and a constant channel size of 400. And each one of these lines is representing the amount of clustering, so in different intermediate layers. So this is the first layer, the second layer, and so forth. And we take varying depth and train the same network. And what we see is that the clustering monotonically increases until we have some saturation. So after something like 7 layers, we're already getting collapse. And we see that the saturation happens the same in each one of these networks. So we get the intuition that this collapse metric actually helps us understand how many layers the network actually needs to fit this data set, and the top layers are redundant. So I'd like to formalize this just a bit. So we have a training set S, and it's composed of these SCs, and these are all samples of class C, and a mapping from the input space to an intermediate layer. So we can define our trained class means mu f of SC, just the mean embedding in this intermediate layer of all samples from class C. And we can define the nearest class center classifier, or NCC classifier, H hat. And it's going to go like this. We're going to take a sample, we're going to run it into this intermediate layer, and we're going to ask what's the closest trained class mean. And this is a decision rule, so we can actually look at the test and train error rates and the accuracies. And what neural collapse basically says is that in the penultimate layer, this NCC classifier is going to be identical to the network decision. So now we're able to define our effective depth. So let's say we have a trained neural network of L layers and a classifier at the end. And we're going to define Fi as the network up to layer I. And we're going to define the NCC classifier just like we did before. So the epsilon effective depth is going to be the minimal layer at which this NCC error rate is going to be smaller than epsilon. So we have this clustering going up, and at some point the error is less than epsilon. Now, why does this definition make sense? So this is something we discover in our paper, which we call the minimal depth hypothesis. And what this basically tells us is that there exists some integer L0, such that if we train a neural network of depth greater or equal to it, and we do it again with cross entropy using SVT and weight decay, the effective depth is going to remain constant. So it's going to be L0 no matter how many layers we stack on top of it. So going back to this figure, we have this L0 when it collapses, so something like layer 6. And if we add more layers, we're actually going to collapse in the same place. So we have this minimality through this metric of neural collapse. And how can we use this minimality for generalization? So we use an observation which is quite intuitive and which we see in practice, is that training with random labels, fewer layers reach collapse. So intuitively, if I take a data set and I ask how hard it is to cluster it into two centroids, and then if I take some of the labels and I give them random labels, this is going to be harder to cluster, and therefore we'd expect more layers. And this is exactly what happens. So here I have the same setting. We have a convolutional neural network with 10 layers and 400 channels in every layer. And we look at different noise ratios. So this is noises for the labels. And we see that if we take, let's say, epsilon 0.03, so we see that in the 0% noise, we have collapse after 6 layers. In the 25% noise, we get collapse after 8 layers or 7 layers. And in the 75% noise, we get collapse only in the final layer. So we get the feeling that this metric somehow tells us how much the network is ruined when we corrupt the labels. So how can we use this to actually show generalization bound? So this is something we call the comparative generalization bound. But before this, I'd like to take a minute to talk about traditional generalization bounds. So let's say we have a classifier H. We say that with probability 1 minus delta over some training data S and a sample size M, the error of the distribution is usually bounded of something this form, which is the error on the train set, plus this form right here, where C of H is the complexity. So it could be the VC dimension, some parameter counting scheme, more recently, the norms of the weight matrices, plus this log 1 over delta term, and divided by the number of samples. Now, usually this is going to be, so we want this to be minimized by the training algorithm, either implicitly or explicitly. And the error on the train should be small because we want to sort of fit the data set. But the problem is that in deep neural networks, this complexity term is quite large. So the number of parameters is huge and usually much bigger than the sample size. And therefore, the bound we get is vacuous in this setting. So let's talk a little bit about our setting. We have some hypothesis class, so some neural network. And we have some complexity measure of this classifier. So you can think of the effective depth here. And we define the minimal complexity for a data set S as the minimal complexity of a classifier that fits this data set. And we're going to need one more thing for our bound. And this is that something we call uniform mistakes. This says that the learning algorithm on a train set for a train and validation set makes mistakes over the validation set uniformly. So both the values of the mistakes and where it makes the mistakes is distributed uniformly. And given this assumption, we can show our bound, and it goes something like this. So we pick some noise level P between 0 and 1/2, and we have some training set and validation set from the distribution. They're both of size m. And we assume that the learning algorithm has uniform mistakes on the validation set. And let's say we train a classifier on the training set with gamma initialization. And we define y validation tilde to be the y val labels when we corrupt pm with them. So if p is equal 0.2, we're going to corrupt 1/5 of them. Then we can present our bound. So our bound in expectation of the error on this classifier on the distribution is bounded by these two terms. So let's break it down. This term is going to be the corruption level that we chose. And then we're going to have this probability. So in this probability term, we compare two quantities. So this is why we call it the comparative bound. We compare the expectation of the complexity of this classifier over different initializations with the minimal complexity needed to fit this corrupted data set. So let's look at some examples of this. So if we take, let's say, a large P, so we corrupt our data set a lot. So this term is going to be quite big. However, this data set is going to be very corrupted. So we'd expect that the complexity of our classifier is going to be lower than the complexity needed to fit this noisy data set, and therefore this probability is going to be small. On the other hand, if P is close to 0, so very small, this term is going to be small, but this validation set is going to be very close in distribution to the training set, and therefore the complexity of this classifier is going to be bigger than the minimal complexity needed to fit this data set, and therefore this probability is going to be large. So we get this interplay between the ratio and this comparative term. So this holds for different complexity measures, but the effective depth makes a lot of sense. This is because it's a discrete measure, so we can actually check different values and see when it holds. And this is versus a continuous notion of complexity for, let's say, the minimal weight norms or something like this, where it's hard to estimate the minimal norm needed to fit this data set, for example. And we also have the minimality hypothesis, which in our bound tells us that if we add more layers, the bound doesn't grow. And this is something very convenient for bounds. This is something we'd like to have in general for bounds. Cool. So we have initial experiments with this bound. So we actually estimate it. We do it for MNIST, Fashion MNIST, and CFAR10. And here I show for convolutional neural networks of depth L and 8 channels. So we actually have in the papers more examples. And for each one of these architectures, we have some, this is the actual test error. And we guess different P's, right? So different P's give us different bounds. And we actually get pretty nice bounds. So 0.1 for MNIST, 0.2 for Fashion MNIST, and 0.66 for CFAR10. And this is quite nice since these are very deep neural networks and we actually get non-vacuous bounds, which are relatively tight. So there are two other things I'd like to show about our bound that I think are pretty cool. So the first, we said that this bound generally shouldn't increase when we add more depth. So this is exactly what we test. For example, for MNIST, we earlier saw with 10 layers, so we look at 12 layers and 15 layers, and we see that this bound is maintained. And this is the same for other architectures. In CFAR10, it actually gets better. So this is something interesting and I guess a bonus. And another thing I'd like to show is that we actually compare it with some well-known bounds in the literature. And these bounds rely, some of them, on the norms. These are quite big in practice. So the best one is the spectral Frobenius norm, and it's quite vacuous for these networks. And generally, there's a trend of them getting bigger as we add more depth, which is something that our bound is able to circumvent. Okay, so future work includes finding different complexity measures for this bound and seeing how we can approximate them. We'd like to incorporate the width and see how it interplays with this neural collapse setting. And potentially, we'd like to prove the minimal depth hypothesis and see how we can show it theoretically. So I'd like to thank my collaborators, Tomer Galanti and Liam Galanti. And yeah, thank you for listening.
Thank you so much. Do we have any questions from the audience? Yes.
So there was this assumption on the uniform mistakes. I was wondering if that actually
Excuse me, I can't hear the questions. So is it possible to say it with a microphone or something like this?
Yeah, sorry about that.
Thank you.
So there was this assumption on uniform mistakes on the validation data. It seems a little strong to assume. So is that first like verified in practice? Like how, do you have any understanding on how strong a condition that is to require?
Yeah, that's a great point. So you're right. This is maybe the only assumption here we take that it's a little bit harder to show. We haven't yet done experiments to show this in practice. We do think that it would make more sense on some data sets versus others. So for example, in things like hierarchical data sets, it might make less sense, right? Because you'd have two classes that are more similar in nature than other ones. But yeah, this is definitely something we'd like to show that happens in practice.
Just to follow up, so is there any link between like an assumption on the data distribution? Are you also assuming that there is some form of uniform measure for all the class marginals?
Yeah, we don't make actually assumptions on the data. So the nice thing about this comparative bound is that we compare how the network behaves on the data set with how it behaves on the corrupted labels of the same data set. So this sort of implicitly includes this info on the data set, if that makes any sense.
Right. So if the data was very skewed to begin with, then to ask a learning algorithm to have uniform mistakes can be near impossible, right? Like if I see 100 examples of class A and only 2 examples of class B, then but in validation data, like what is the uniform mistake here? I mean,
yeah. So I guess there's two parts here. So we do assume that the data set is balanced. So just in terms of the very skewed. But I guess if the data set is very problematic, yeah, then maybe the assumption of the uniformity on the validation set might be less sensible, but I need to think about it. I'm not sure.
Okay, thank you for your time. Yeah, thank you for the talk. Yeah.
Let's thank the speaker again. Thank you.